Hi.
Hi, are you sure this course is just for 2499?
Yes, and you know this is the only course with this expertise across the world.
No way!
Yes way. Don't delay. Enroll now.
Geeks learning together.
Okay, so hi everyone. This side Ayush Tripathi, DSA mentor and problem setter at Geeks for Geeks, and I welcome you all to this post analysis of the last problem of the day, which was named as word search. So let me check that whether I am audible or not. Can someone just please confirm that whether I am audible or not? That whether I am audible or not. Okay, so everything seems good to me. So, how many of you are able to solve the problem? Okay, hi Rishit. Hi Amar Sai. Okay, so I guess you guys are ready to move forward. So, let me just share my screen first. Okay, so hope the screen is now visible to you. So, the problem name was word search, and basically, in this problem, we have a 2D board of letters and a string word, and our task is to check that whether this string word is exist in the board or not, and if it is exist then we have to return true, otherwise we have to just return false. And the word can be constructed from the adjacent cells, that is horizontal and vertical neighbors of the cell. So let's take this example. Here the size of the board is 3 cross 4, that is we have 3 rows and 4 columns. So let's just move to the board, and the word is geek, and our task is to check that whether this word geek is present in this board or not, and here it is present, this one, geek. You can see here all the cells are adjacent to each other, or actually not adjacent to each other but somehow adjacent to each other. That is, this G is adjacent to E, then this E is adjacent to this E, and this K is adjacent to this E. So we found our word geek in the board, so we simply return true. So is the problem statement is clear to everyone? Can someone just please confirm? Okay, so I guess we are audible. Okay, thanks, Rishit. So is the problem statement is clear to everyone? Okay, clear. So now let's just move to the solution. And to solve this problem, you just need a single observation. And the observation was that you just have to visualize this board as a graph, and then you have to just apply the DFS and visualize every cell as a node, and the edges are its neighboring cell that are either share its vertical line or horizontal line. So before visualizing this matrix, we can say, as a graph, let me just give you the quick overview of the graph and the DFS traverser. So graph is basically the combinations of node and edges as a connected component. So let's say we have this graph 1, then there is an edge from 1 to 2, then from 1 to 3, then from 2 to, we can say, 5, then from 5 to 6, then from 3 to 6, then 7, 8. Okay, so I guess now we have enough node. So now we have to apply the DFS in this graph. So DFS is nothing but the depth first search. That is, we visit all the node in the same order, and we do not visit the node that we have already visited. So let's say we start our DFS traversal with this node 1. So we visit all its neighbor. We cannot jump to its child, that is the child of child. We cannot directly jump onto this 5 because there is no connection between 1 and 5. So we first have to visit its parent, and then from its parent we can visit its parent, its child. That is from 1 we first go to 2, then from 2 there is an edge to 5 and 6. So we first visit 5, but there is an from 5 there is an edge from 2 as well, but we cannot visit 2 anymore because we have already visited the node 2. So from this 5 we visit 8, and from this 8 we visit 7, 6, and so on. So basically we visit all the neighbor of the current node except the node that has already visited, and this was actually the DFS traversal. But how do we check that whether we have already visited the node or not? So for that we simply declare a visited array, and using which we keep track of the nodes that we have already visited. All right, so just wait for a second. All right, so here what I have just said, that we in a DFS traverser we visit the neighbor of every node, but we do not visit the nodes that we have already visited. And how do we check that whether the node is already visited? So for that, in a graph we declare a array in which we store the information that whether the node is already visited or not. And if the node is already visited, then we mark the value of that node in the graph as true. And if the value is true, then this means the node is already visited. So we declare a vector of bool, and this bool vector will simply denotes that whether the node is already visited or not. So if visited of I is equal to true, then this means node I is already visited. All right, so this was all about the DFS traverser. Now let's just see how we relate this DFS traverser with the given matrix. So let me just quickly recall the problem. So here what we have given. So we have 2D matrix of characters and a string word, and our task is to check that whether this word is present or not. And we are only from the cell, we are only allowed to move to its neighbor. So what we will do, we we visualize this matrix as a graph, and every cell as a node, and its neighbor as the and its neighboring cell as the neighboring node in the graph. So what I mean by this, so let's say we are currently considering this cell. So what are the neighbor of this cell, or we can say node? So these are the four neighbors of this cell, because from this cell we can only visit its neighbor which either share the horizontal boundary or the vertical boundary. So these were the neighbors of this cell. So we simply start from every cell and then recursively move to its neighbor cell, and we check that whether this word is present in the board or not. So what I mean by this, so using this key idea, what I have just said, that we consider every cell as the starting point, that is for I is equal to 0 to n minus 1, and here n is the number of rows in the matrix, or we can say board. Then for j is equal to 0 to m minus 1, and here m is the number of columns in the matrix, and then we simply call the dfs recursive dfs function, dfs, with this cell, that is I comma j. All right, so now if I consider this example, and let's say we start our dfs traverser with this node. So currently we are at this node. So then we simply check that whether the current character is matches with the corresponding character in the word, in the string word or not. And if they do not match, then I simply return from the dfs call, the word because the word cannot be start from this cell. So I simply return from here, or we can say simply return false. That is, this cell cannot be my starting point. And if it is true, that is, if this cell matches with the corresponding character in the string word, then I just call the recursive function for all its neighboring node. That is from this node, let's say I comma j, cell I comma j. So from this I comma j, we have four neighbors, that is I plus 1 comma j, that is we can move to its bottom cell, which is this one. All right, and the next neighbor is I minus 1 comma j, that is we move to the cell which is above this cell, that is this one. And the next edge is I j plus 1, that is the cell in its right, this one. And the last neighbor that we have, or let me just write over here, and the last neighbor that we have is the cell in its left, that is I comma j minus 1. And then we simply call the dfs function for these neighboring node. And also we have to mark this current cell as true, because we are not allowed to include the cell multiple time. And even this thing was mentioned in the problem statement as well. You can see here the same letter cannot be used more than once. So that is, our word cannot be consist of this particular e more than once. So is this approach is clear to everyone? Please do write a +1 in a chat. Okay, okay, thanks Rishit. Okay, so now let's just see how we implement this. But before implementing the solution, and now I want to discuss that how do we keep track of this thing, that whether we have already visited the cell or not. So in the DFS traverser, here we have declared the visited vector to keep track that whether the nodes are already visited or not. So what I mean by this, so when you move from this one to its child 2, and then you start processing the neighbor of node 2, then the neighbor of node 2 is node 1 as well, but you have already visited the node 1. And to avoid the infinite recursive calls, here we have declared the visited vector to check whether the node is already visited or not. But in this case, you don't need to declare a vector or array to check that whether the node is visited or not, because that was definitely kind of inefficient. So rather than declaring a 2D array, we manipulate the character of the board with some special character. So what I mean by this, so when I move from this cell to its neighbor, that is from this cell, when I move from this cell to its neighbor, so before moving to its neighbor, I manipulate the value at this cell, so that in future none of the character get matched with the character in this cell. So I manipulate the character at this cell with some special character, or let's say hash. And we know our string word only consists of the lowercase English alphabet. So this word does not contain the special character hash. So there is no chance of including the cell anymore, or we can say there is no chance to visit the node again. So this was all about the explanation and observation. Now let's just see how we implement this, and also let's discuss the base cases first. That is, what are the base cases? So we have to match the characters of the word from the characters in the board. And so for that, we simply keep track of the indices of the characters in the word, and we start with the zeroth index. And then if this character get matched, then for the next recursive DFS function, we increment the index. So let's say this information was stored in some variable index. So when I call the DFS function for its neighbor, then I simply increment the index to match the next character. That is, index is now pointing at this character. All right. So now let's see how we implement this. All right. So let's just first take the size of the board, that is int n is equal to board dot size, and int m is equal to board of 0, that is the number of columns in the 0th row, dot size. And then I simply iterate over each cell and consider each cell as a starting point, and then simply check that whether we can form the word in the grid or not. So for int I is equal to 0, then to n minus 1 because of the zero base indexing, that is less than n. Then for j is equal to 0, and here I denoting the row number and j denotes the column number, j plus plus. And then I just call the dfs function, and the dfs function will simply return the boolean value, that is true or false. And if it is returned true, then this means that the given word is found in the board. So if dfs, and then if dfs function returns true, then I just return true, because now we don't need to check for the other cells. Return true. And after considering all these cells as the starting point, and and if we do not get any possible solution, then I just simply return false. That is after considering all the possible cases. If we do not found the word, then I simply return false. Now let's just see how we implement this dfs function. So the return type should be bool, that is dfs. And what are the informations that we need to keep track? Okay, so the very first information that we need to keep track is the information of the current cell, that is I and j, row number and column number. So int I, int j, and then our code to extract the character at the current cell. So let me just copy it over here. And here I am passing this board as the reference, so that the recursive function do not make the copy of this 2D vector. So that's why using this AND operator. And then the index variable, which will simply denote the current index in the string word index. And this string word as well to extract the characters, and again passing it by reference, so that the recursive calls do not make copy. Now here we start with the current cell, that is row I and column j, and again our board. Then from which index we start? So we are considering this current cell as the starting point. So the index should be start with 0, and then our word. Then what would be our base case? So the first base case that we have, when the index is equal to word dot length, that is we have matched all the characters from the word in the board. In that case, we do not have any other character to match, so I simply return true. So if index is equal to word dot size, then I simply return true. And what is the other base case? So the other base case is that when the current cell is invalid, but you might think that we are calling this dfs function in the appropriate limit, that is I is less than n and j is less than m, but we blindly make the recursive call for its all four neighbors. So this function will simply, so this base case is just for that, that is if I is less than 0 or I, and instead of writing using this keyword or, you can also use the or operator, but I generally prefer to use the keyword or. This makes more sense to me. So if I is less than 0 or I is greater than the n, all right. So, and here n is nothing but the board dot size. or j is less than 0, or j is greater than or equal to the number of columns, which is m, or we can say board of 0 dot size. So let me just copy it. So board of 0 dot size, or, and what is the other case? When the character at the current cell does not match, do not match with the character in the at the current index in the string word. In that case, we cannot start with this cell. So, or what we can say, board of I comma j not equal to word of index. In that case, I simply return false. That is, this cell is not a valid cell. All right. Okay. Otherwise, I simply manipulate the character at this cell. That is character. But before that, before the manipulating the value, we have to somehow, we have to store the value at this cell, because while tracing back, we have to revert the revert the information at this cell. So what I mean by this, so in the dfs call, I have manipulating the values before calling its neighbor. So let's say we start with this cell. So when I call the dfs function, I manipulate this value. Okay, so when I call the dfs function to its neighbor, I manipulate this value so that this value do not get include multiple times. Then I call the dfs function for this cell. Then again I manipulate the value. Then I call the dfs function for this cell. Again I manipulate the value. Then again I call the dfs function, and again I manipulate the value. So let's say this was the invalid cell. So from this invalid cell, we know that this path is not a valid, but there might be a case when this path is valid, but you have manipulated the value, so you cannot move forward from this cell to this one. So that's why while returning from the dfs call, we have to revert back the information of the cell as it is. That's why here I am first storing the character at the current cell, then manipulate the character at the current cell. So character at the current cell, that is board I comma j. Then I just manipulate the value, that is board I comma j is with some special character, or let's say hash. All right, and then I call the recursive dfs function for all its neighbor, that is bool our result is equal to dfs of I plus 1, that is cell in its the bottom cell, then same j, and then board, then index plus 1, because we have matched the character at the current index, so we have to move to the next index in the word, that is index plus 1, and then word. All right, or the next neighbor is at the cell I minus 1, that is the cell at the top, this one. So let me clear this. So let's say we started from this cell. So these were the four neighbor. So this was nothing but I minus 1, comma j. This was j minus 1. This was I plus 1. And this was j plus 1. These were the four neighbors. So I minus 1 or j plus 1. J plus 1 or okay, or j minus 1. That is the cell in its left. All right. And then while returning back from this current recursive call, we have to revert the information of the current cell. So I simply update the character at the current cell with the character that was previously there. That is board I comma j is equal to c. Here we have stored the character in the variable c, and then I just simply return our result. And if this result is true, then this means we have found our word in the board. So I simply return true. Now let's just try to run this. Okay, same as the expected one. Now let's try to submit this. Okay, accepted. So is the solution clear to everyone? Please write a +1 in a chat, and then we discuss the time complexity and the space complexity. Okay, clear. Thanks, Rishit. So can anyone try to guess the time complexity for this solution? Time complexity. Okay, the approach has n square time complexity. Okay, n square time complexity. So actually the I'm not getting what actually n square, because even the size of the board is n cross m. So writing n square is not that much clear, because from each cell you have explore the entire board in the worst case. Yes, Rishit, makes sense. So the time complexity is n cross m. So the time complexity is n cross m, but this n cross m is only of this for these two for loop. What about this DFS function? What about this DFS function? What is the time complexity for this DFS function? Okay, any guess? So if you observe this DFS function, or we can say recursive function and DFS function, both are these similar things. It's just the matter of your visualization. So here you can see here, for every DFS function, we have four options. That is, we have four neighbor. So we calling this function for every cell, we are calling this function four times. All right. So the time complexity for this DFS function, okay, in the worst case, the DFS function will explore the entire board. Okay, makes sense, but not up to that mark, Rishit. Okay, let me tell you why. But before that, let me tell you the time complexity for this DFS function. So the time complexity for this DFS function is 4 to the power length of the string word, because at most you visit these many cells up to the length of a string word, and for every cell you have four options. And Rishit, you are saying that the DF in the worst case DFS function will explore the entire board, but actually not true. Actually exploring the entire board multiple times, because we are reverting back the information. So what I mean by this? So let's consider this example. So let's say you have started with this cell. So you first explore this path, and you do not and let's say you did not find the answer. So in next time you explore this path, then in next time you explore this path, then in next time you explore this path, then this one, then this one, then this one. So you can see here we are exploiting the entire board again and again. So the time complexity is 4 to the power length of the string word. This is the time complexity. And what would be the worst case? So in the worst case, all the characters in the guild are same except the one. So what I mean by this? So in the worst case, so let me erase all these characters. So the number of rows are n and the number of columns are m. So in the worst case, all the characters are same. That is A, 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 and let's say A. All right, A except the one. Or let me write this character as some other character. Let's say B. All the characters are A, and your word is equal to n into m times character A. So for every starting cell, you explore all the path, and whenever you reach to this cell B, you found that the character not match. So you simply return false. That is, you first explore this path and you return false. Then next time you explore, what we can say, you explore this path and return false. Next time you explore this path and return false. Or so you can see here there are multiple paths. We are exploring the entire grid multiple times when we starting from the first cell. And similarly, when you start from this cell, you first explore, or not this one, but this one. Then here you can see here you did not find your word in the gate. Next time you explore this path, then this one. So you can see here from this starting cell again you are visiting the entire board again and again. So that's why the time complexity is 4 to the power the length of the string word. So I hope this makes sense to everyone. For this problem, GFG has weak test cases. Okay, yes, Chinmay, I noticed this thing that the test cases are quite weak. Even you don't need to use the this visited technique. So we definitely fix this very soon. Just stay tuned for that. So I hope the solution was clear to everyone. And in case if you have any doubt, then please write down in the chat, or we just wrap up the session. Okay, so thank you so much everyone for joining the session. And in case if you have learned something new, then please hit the like button. And your feedbacks are really important for me. It helped me to improve the upcoming sessions. So thank you. Okay, but before ending this stream, I forget to share this code. Sorry guys, my bad. So let me just quickly share the code. So GFG ID. So let me just copy this code, or let's just copy the entire class. Okay, all right. So thank you everyone.